Good afternoon, everyone. Welcome to the second RISE seminar of the semester. Today we have Ruoxi here, who's a postdoc in Don Song's lab. She completed a PhD at Berkeley a couple of years ago, and her work she has won a bunch of fellowships during a PhD, and her work has been prominently featured in some media outlets. And today she's here to talk about her work on creating a data economy. And without further ado.
Okay. Yeah, thank you, Sammy, for the introduction. Hello, everyone. I'm really glad to be here. Today, I'll be talking about some of the theory and algorithms that I developed over the past few years towards the goal of building a equitable and trustworthy data economy. So data is the main driver of value in the current economy. It has created a lot of intelligent products, transformed our infrastructure, and created new businesses. But there are some new challenges that we need to address. The first challenge is that there has been a pressing need for data valuation. There has been a couple of bills that are proposed several months ago to enforce tech companies to quantify the value of the data that they collected from their users. And locally in California, Governor Newsom also proposed this data dividend, whereby users are compensated by the data that they contribute to the tech companies. As we go forward, the need to value data is going to be more and more prevalent. So if you are a data consumer or data vendor, you might be interested in knowing what is the price of the data you are buying or selling. If you are machine learning practitioners, typically you have data from different sources. You want to know how to collect more useful data and what should be the sources that we need. And if you are policymakers, you are interested in knowing how to litigate and how to compensate users when there are massive data breaches happen. However, the core question is that it is never clearly defined what is the value of data and how do we quantify it operationally. The second challenge is that because of this ubiquitous data sciencing, we have great privacy concerns. This is smart meter data taken from a household, and you can see it is fairly easy to know when the family are on vacation and when they are at home. Indeed, this information has been exploited by some burglars to decide when to break in. Aside from privacy concerns and the need for value data, another challenge is that we can't really trust the data-driven decisions because oftentimes they could be unreliable. So we know that this is an example where a panda, by adding some imperceptible noise, it is classified as a given by a neural network with high probability. And there are other type of attacks where attackers inject some bad data into the training set in order to manipulate the performance of the machine learning system. So in this case, all the people that wear white hat are classified as Alice. So what can we do about it, and how can we know if the data point has already been corrupted? So to solve those challenges, the goal of my research is to develop some theoretical foundation and practical algorithms for building an equitable and trustworthy data economy. And towards that goal, I have been working mainly on three areas: data valuation, data privacy, and adversarial learning. So I will give you some highlights of my work in each of these three areas. For data valuation, the first thing that we did is we tried to quantify try to define the problem and see what it means to value data. And we are actually the first of a group who really formalized this problem. And secondly, we developed some really practical and scalable algorithms that can value data from millions of data contributors. So we have been collaborating with Stanford Hospital as well as some system researchers and try to build this data marketplace for medical data in order to incentivize patients to share their data to medical research, and they will get rewarded when their data are used. Aside from that, my algorithms are also being integrated into a real-world data marketplace called FOAP, and the idea is to price the data and when the data is used for training machine learning models. For data privacy, my work has been largely focused on smart energy systems, although the implications goes beyond the energy systems. So we have been trying to develop some attacks that can be used to assess the privacy risks in energy systems. And we also develop some algorithms that can be used to optimize the privacy and the utility when we try to add privacy into the system. And we also deploy it into practical systems. For For instance, we have demonstrated the first privacy-preserving temperature control of a smart office at UC Berkeley. So the idea is to add some noise into the sensor measurements so that they can be used to infer location, private location information of the occupants. And the noise designed into with the right amount so that it can be still useful to control the building. And we are actually the first of the group who really look into the privacy problems in energy system systematically. My work has led to initiation of various privacy-related projects in an international building and energy program. For adversarial learning, we have proposed some new attacks and new defenses. My work has exposed some new vulnerabilities, and we also achieved some state-of-the-art results to detect anomalous data. So let me talk about some of the work that I have done in each of these areas, but most of my time will be spent on my recent work about data valuation, but I will mention some highlights and ideas for the rest of the two areas as well. I will conclude with some future directions. So let's start with data valuation. There are some natural ideas to value data. For instance, you can value an aggregate data set based on the amount of queries that you performed on the data set. You can also design some auctions to value data. You can even train a machine learning model to predict the data price based on some attributes like data age and so on and so forth. But the common problem with this approach is that they can't really handle the problem, handle the case where your data set comes from different individuals. The problem there is that how can we pay each individual in a proper and a fair way. So I want to motivate some properties that we want to have for data valuation techniques. So I mentioned that we have collaborating with this full data marketplace. So they have a lot of data available on their platform, and the company is envisioning to build a model marketplace. Imagine you have someone who say, I want to train a cat versus dog classifier using all the cat and dog images available on this platform, and I'm willing to pay $100. And at the end, this model buyer will get a model trained over 1.5 million images available on this platform. And the technical question that we want to solve is that how can we distribute this $100 back to all the data contributors? So a natural idea to value data is just to assign some uniform value to every data point. But if you take a close look at this animal, it isn't a cat. So there are a lot of images that are mislabeled. And we really need to design a valuation mechanism that can fairly distribute value, and we want some actability property. And secondly, there are so many images. Practical machine learning models often involve millions of data contributors, so we really want some algorithm or technique that are truly scalable. And aside from that, data value also has some unique properties that we need to consider. For instance, as I mentioned, the data often come from different sources, and the value of one source data really depends on the existence of other source. So there is some combinatorial analysis that we need to do in order to figure out the value of data. And secondly, this is the best accuracy achieved on ImageNet every year, and you can see that machine learning progress is very fast. You can, on the same data set, you can either use it to train a dump classifier or super classifier that can achieve performance surpassing human beings. So the value of data is really outcome dependent. It really depends on how we use the data and what model we use it to train. And thirdly, unlike other commodities, data is infinitely useful. And if you use it more, the value will aggregate. So we need to consider this cumulative aspect into our data valuation framework. So our work is one of the first who really combine all these aspects into a unified framework and come up with a notion to value data. So we first focus on the combinatorial property. This inspires us to model machine learning as a cooperative game. So by modeling it as a cooperative game, we try to model the interplay between different data sources. So how can we model machine learning as a cooperative game? There are two components in cooperative game. One is players. The other is utility function that measures the profit that's generated by any subset of players. So in the context of machine learning, the players will be all the training points that we want to value. And in machine learning, these training points will be fed into some learning algorithm to produce a model, and then it will be evaluated against some validation set to produce a performance measure like validation accuracy and so on and so forth. So the utility function in the machine learning context is a function that maps any subset of training images to a performance score. So it measures the performance of the model trained on any subset of images. And then we look at this outcome dependence property. This inspires us to reduce the data valuation problem to the problem of profit allocation. So we want to allocate the profit generated by machine learning model to different data contributors. The more profit we get from machine learning model, the more profit data will, the more value data will have. And then we look at the rest of the two properties and ask, what is the profit allocation scheme that satisfies these two properties? It turns out that in cooperative game theory, there is a unique notion that satisfies these two properties. That is called the Shapley value. It was proposed by a Nobel Prize-winning economist in Lloyd Shapley in 1950s. And he proved that this is a unique solution that satisfies these two properties. What is the Shapley value? I'm going to define it in the context of machine learning. Imagine you have a size n data set, and the Shapley value will assign a real value score to each of the training data points, so that the sum of the value will be equal to the total performance of the model trained on this data set. And here, if you want to compute the Shapley value of the S data point, and here is how it is defined. So N is number of training points, and D is the training set we want to value, and S is any subset of this training data set excluding the data point we want to value. And U is a utility function. It will be validation accuracy or some other application-dependent metrics. And if you take a close look at the terms in the bracket, you'll find that actually this measures the marginal contribution of the point we want to value to any subset in this data set. So the intuition about the Shapley value is that it really measures average contribution of a data point to any subset in the training set. So I mentioned that the Shapley value has some cool properties like equitability and cumulativeness. So let's take a look at how it is defined mathematically. So the Shapley value is equitable because if we consider two data points and adding them to any part of the data will lead to the same model performance, then they will have the same Shapley value. And if we consider a data point and adding it to any part of the data set, it wouldn't change the model performance. Then it will have the zero Shapley value. So those are guaranteed by the Shapley value definition. And as for the cumulativeness, it basically means that if we use the data for multiple times and each of the used data is associated with some performance score, say U and V, then the value that I get from the two use of the data will be equal to the value that I get from each use of the data. So this is really nice because it allows us to add up the value that we get from each use of the data. So here is an illustration of how we can compute the Shapley value. Imagine we have a training set with 3 data points, and we want to compute the Shapley value of the last data point, the fish. So what we do is that we look at the rest of the 2 data points and consider all possible subsets that can be formed by these 2 data points. And then we add this fish to any arbitrary subset and compute the marginal contribution of this fish. And then assign it with proper weight dependent on the size of the subset. And then we divide it by the number of the size of the training data. And that gives us the Shapley value of this fish. So the Shapley value is really nice. It has its cool properties. But the challenge of using it is the computational challenges. Firstly, you can see this sum here involves summing up exponential number of subsets. So for each term in this sum, we'll need to evaluate the utility function. And if we consider the Shapley value in the context of machine learning, it will even getting worse because evaluating this utility function itself requires us to retrain a model on the subset of the data and then evaluate its performance. So we can't really afford to retrain our model for exponential number of times. So this is clearly intractable. the existing work to tackle the computational challenge is really to treat this definition as the expectation of the marginal contribution of some point to some random subset. And we want the distribution of the subset to matches the factors in the front so that these two lines are equivalent. And then we can simply adopt some Monte Carlo methods to approximate this expectation. What we do is that we can randomly draw some random subset from the distribution and then compute the marginal contribution and take a sample average. So yes?
So a couple of related questions. So I understand that taking the average over all subsets gives you the properties of the Shapley value. But someone could make the case that what you want is actually not all subsets, but you just need to take a maximum of all subsets. So that's one thing. And the related question is, can't you just take everything except the ith data set, the ith data point, everything, so it's a leave one out system, and that will also make it computationally a lot simpler?
Sure, yeah. So that's a great question. So actually another way to value data is just to compute the leave one out arrow of a data point. But there are some problems. Firstly, it does not satisfy the desirable properties that we want. And secondly, as I will show later, when we try to use it to value data importance experimentally, it will be less indicative of a real data importance than the Shapley value. Yes?
Are there any, especially looking at that difference between U with VI and without, are there any numerical issues involved?
So we haven't.
Yeah,
you mean like when these terms are too very close, then we have.
Not even counting the cost of computing.
So computing this utility function will be very expensive in machine learning because it is a performance score, and to compute the performance score, we need to retrain the model on the subset of data point and then evaluate against some validation data point. So yeah, it's very expensive.
And the difference could be quite small.
That could be quite small, but we didn't really consider this numerical issues yet. So this is a state-of-the-art way to handle the computational challenge of the Shapley value. So there is a long line of work that adopts this method. So to evaluate what's the performance of the approximation method, we can see that the estimated Shapley value is an epsilon delta approximation to the true Shapley value S if the maximum difference between these two across all training points is bounded by epsilon with probability at least 1 minus delta. So the previous work showed that in order to achieve epsilon delta approximation, you will need n log n and utility evaluations. So essentially you need to draw like n log n number of subsets to achieve this approximation. So clearly in machine learning context, we can't afford to retrain our models for this number of times, so we fall into a problem. So next I will talk about some algorithms that we designed to really make the evaluation of the Shapley value scalable. The first idea that we have is, can we make the Monte Carlo method better? The answer is yes. So actually there are some characteristics that we can use to make the Monte Carlo method better. For instance, in Monte Carlo method, if you consider it, actually the random subset are used independently. You just take a sample average. But the idea is that if you have a data point that has high value, it tends to boost up the utility of all subsets that contains this data point. So there are some information sharing between different random subsets. So we leverage this information sharing and design an algorithm that only requires log n squared number of utility evaluations while achieving the same error guarantee. So this is really a large improvement. If you consider a large number of players, so our method can be orders of magnitude faster than the existing one. So what's cool about this method is that it is not limited to data valuation. It can be used to any general profit or cost sharing problem. But the problem is that in machine learning context, we still cannot afford to retrain the model for log n square number of times. So what can we do? How can we avoid retraining models while still being able to compute the Shapley value? So our key idea is to leverage some characteristics of utility function that naturally arise from machine learning context. Let me give you some examples. The characteristics really depend on what learning algorithms you can use. So if you use k-nearest neighbors, the utility doesn't really depend on all the training points in the database, but rather some k-nearest neighbors. So we call it locality. And if you use some differentially private learning algorithm, you have this stability guarantee, meaning that removing or adding a data point into the data set wouldn't change the model performance so much. So intuitively, you will have value uniformly assigned. So in this talk, I'll be focused on how we use locality to design a really scalable algorithm. A quick overview of k-nearest neighbor. So in k-nearest neighbor, we start with a training data set. So if we want to predict the label of a query point, so what we do is that we first sort the training data according to the similarity to this query point. And then we take a majority of the labels in its nearest neighbor. Let's focus on the simplest case and try to get some intuition why k-nearest neighbor can have efficient valuation algorithm. Let's say k equal to 1, and we consider a natural utility function that can be defined for one nearest neighbor. So this utility of a subset is 1 if the label of the query point agrees with the label of its nearest neighbor in S, and 0 otherwise. So this is really natural because it basically evaluates the accuracy of the k-nearest neighbor that can be trained on the subset of subset S of data. So let's say we have a database that are sorted according to their similarity to the query, and we want to compute the Shapley value of this cat here. And we need to consider its marginal contribution to some random subset in this database. Let's say the subset is this one. And if you think for a little bit, you will find that actually adding this cat into this subset wouldn't change the utility. That is because all the elements in this subset are closer to the query than this cat. So the decision, the prediction has already been determined by this subset. Adding this cat wouldn't change the decision. And similar for some other subset in the database. So the key idea is that instead of naively going through all possible subsets, for a large number of subsets, this utility difference is actually 0 because of this locality property of k-nearest neighbor. So using this property, we design a very fast algorithm. So our algorithm is to first sort the database according to its similarity to a query point. And we consider this utility function, which is a generalization of one nearest neighbor utility that we have seen in earlier slide. So it is quite intuitive. It basically considers, if you have a query point, you count the number of nearest neighbors that have the label same as the query point and take divided by k. And the algorithm will compute the Shapley value from the furthest point to the nearest point using this recursion here. And the total complexity is O(n) because we only need to scan the database for once. And because we need to pre-sort the database, so our algorithm is bottlenecked by O(n) log n. And if you consider baseline, you will need to evaluate the utility for exponential number of times. And then for each utility evaluation, you need to sort the database. So essentially, our algorithm eliminates this exponential factor in the baseline, and this is a big improvement. With the efficient algorithm, for the first time, we are really able to go to some really large database and see what are the Shapley value. So here I give you a snapshot of the Shapley value of different training points in a 100 million database. And on the left side, it is a query point that we value data against. And on the right is the top value training points for each query point. And you can see that if the query point is from the nature class, and all the top value training points all have natural things. So basically, the top value training points will be semantically correlated with the query point. And this means the Shapley value really give you something intuitive. So then the question is that can we do, yes?
How do you measure similarity between points like this distribution space that you're looking at?
Yeah, that's a great question. So for images, we first train a neural network and extract the deep feature representation of each neural network, and then compute the L2 distance on the deep feature representation.
Is there a particular network that you use here?
So it really depends. So for this data set, we use, I have to check, but for CFAR, we can use ResNet and, Yeah, so the next question is that can we do better? So why do we want to need to do better? Firstly, our algorithm requires us to resort the database for every possible query point. And secondly, if your database is really massive, even sorting is already very expensive. So our question is that can we do better than n log n? So here is our idea. This plot is an exact Shapley value of different training points sorted by their similarity to a particular data point. So if the index is small, meaning that their distance is small to the query point, and if we move to the right, we will move further away from the query point. And you can see that the magnitude of the Shapley value decreases very rapidly if we move away from the query point. And indeed, we can prove a theoretical upper bound on the magnitude of the Shapley value. So our idea is, so how about we pick an index, say after this index, we don't really care about the data valuation problem because the Shapley value is so non-essential. And how about we just set them to be 0? And in this case, we don't need to source the database, and we only need to query the top t points exactly. So then the question is that how can we query top t points without sorting the entire database? It turns out in data mining, there is a standard technique called locality-sensitive hashing. So the idea is that we can use some hashing function with a special property that it will map the close points to the same hash code or the same bucket. So if you consider a query point, then with high probability, it will be mapped to the bucket that contains its nearest neighbor. So instead of sorting the entire database, we only need to sort the bucket that contains the query point. So using this LSH, we prove that we can achieve the complexity with this number. So the exponent here is really depend on your data set. It depends on the dispersion of data. And in our experiments, we show that for some real-world data sets, this number is often less than 1. So basically, we have a sublinear algorithm. And if we consider baseline, it's actually the complexity grows quadratically with the number of data points. So I want to highlight that actually LSH is a standard technique in data mining, but it is the first time it is applied to data valuation, and we also use it to prove a novel bound on complexity. Do you have a question?
Question of clarity.
Mm-hmm.
With respect to query points, is there some assumption on the distribution
Mm-hmm.
of query points, and going up to the actual application,
Mm-hmm.
some sort of gradated value of anticipated queries
Mm-hmm.
coming through?
I see.
Is that the case, or is there just an assumption of uniformity, some kind of uniformity assumption?
So here the complexity is for one query point. Yeah, so if you have n query point, it will be like multiplied by the number of query points.
So presumably, like just to add to this question, your utility function is computed using a validation set,
Mm-hmm.
and you're going to repeat this for every point.
Exactly, yeah.
And the assumption is, of course, that validation set represents what you
So maybe also subsidiary question going back to your original workflow there. Validation set, there's no distinction between participation in the validation set and participation in the training set with respect to the value of the data.
Yeah.
Validation
Mm-hmm.
set is just chosen randomly.
Yeah, in practice, we choose some validation, subset of training data as validation set. But here, we only consider the problem of valuing training data. So yeah, it will be a good future work to consider how can we value validation data. And in practice, because the utility often the utility of the model is often dependent on how the model buyer perceives. So he will basically choose some validation set to evaluate the model. So we can also think of this case where the validation set is chosen by the model buyer, and the training data set is supplied by the data contributor. So in that case, it's not from the same data set.
And like similarly, there's no assumption of priors on okay.
No, yeah, this bound is independent.
It's not dog world.
Yeah, it's not. Yeah, yeah. Thanks for the question. Yeah, so let's compare the performance of our algorithm with some concurrent work. There are two. One is from SML. The other is archive preprint. So the largest size of data points that they can value in their paper is 60,000 number of data points. Well, in our paper, we show that we can value 10 million data points in 44 seconds on a single machine. And if you take a look at the scalability, so y-axis is the runtime, and x-axis is the number of training points, and this Monte Carlo method is a state-of-the-art approximation algorithm. You can see that the both exact algorithm and the LSH-based approximation algorithm can be orders of magnitude faster than the existing baseline. So this is really gives us a handy tool to compute the Shapley value. So far I have talked about the k-nearest neighbor. Then someone might be wondering, how about some other models like deep neural networks? So the short answer is that it is really hard to find some property for this black box in order to compute the Shapley value faster. So previous work have proposed some heuristic to compute the value. For instance, you can use leaf-round arrow or design some early stopping criteria to reduce the number of complexity. So our idea is that since we have this efficient algorithm for k-nearest neighbor, how about we use it as a surrogate for deep neural network? Of course, we can't really run KNN on raw image space. So what we do for image is that we first extract the deep feature representation and then compute the KN Shapley value on the deep feature space. So we compare our work with our heuristic with some other heuristic in the existing work. Of course, our heuristic is faster than the existing ones because we don't need to retrain the model. But one common caveat for all those methods is that they no longer have theoretical guarantees, meaning that we no longer know how close our value estimate is to the true Shapley value. But I want to show you that despite the lack of theoretical guarantees, these value estimates are still useful and they are still indicative of the data importance. And you can use it to enable a vast range of applications. For instance, you can use it to detect noisy labels. Intuitively, those mislabeled data will have low importance. So what we do is that we first compute the Shapley value for all the training data points, and then we filter out the data points from the lowest data value. So on the y-axis is the number of data points that we filter out based on the value estimate. And on the y-axis is a number of data points that are truly mislabeled. And you can see that our heuristic can achieve a better detection rate than the other heuristics, including the leaf-round arrow. And using similar idea, you can use it to detect some adversarial training points, which are also intuitively having low importance, and also do some data summarization, or even actively acquiring new data. You want to query some high importance data for your task. And you can even do some domain adaptation by just computing your importance with respect to the validation data set in a new domain. So there are many things that you can do here. As a quick summary, I have introduced a notion for data valuation based on the Shapley value, and proposed several methods, including a better Monte Carlo method that can be used to value data for generic utility, as well as exact and heuristic way to compute the Shapley value for specific models. So data valuation is really nice because it gives us a way to incentivize people to share more data in pristine form. But the question is that, what if people still don't feel good about sharing their data even though they are compensated? So that is a question that I'm gonna answer next. So I will talk about some of the work that I have done for data privacy, and we try to process the data but not leak people's privacy information. So I will be mainly focusing on the system, privacy of the system in taking this form. So we have some computational unit that sends signals from the physical environment, and it also has some actuator that can control the physical environment. The examples are a lot, like smart buildings, smart grids, and transportation systems. So the challenge to consider privacy in those systems is that they are dynamical systems. They are very different from the traditional settings that we consider privacy, like static databases, and the data utility is to estimate some statistics. And in this case, the utility is to control the system, and we really need to deal with the dynamics. And the second challenge is that these systems are oftentimes mission critical. They are our inhabitants. They supply our electricity. So how can we maximize data utility? Our approach is to take an optimization-based approach. Schematically, we first find some metrics for data utility or performance, and we also find some metrics for privacy. And then we cast the problem of privacy preserving mechanism design as the optimization problem, where we try to minimize the privacy loss subject to some performance constraint. So here is an example of how we can use this framework to design some privacy preserving mechanism for smart buildings. So in smart buildings, right now, we have a lot of sensors collecting different data, and those data are often correlated with people's location. So what we do is that we use mutual information between people's location and the sensor measurements as our privacy loss. And we try to minimize this privacy loss subject to the control performance of the building. So using this approach, we can design some privacy mechanism that can optimize the privacy utility trade-off and perform better than some common baselines. So my work has also looked at some other problems arising in this context. For instance, how about, yes?
So just going back to your previous slide, do you have any sense of, that you could get something useful while actually making sure things are private? Because I can imagine that as you lower this performance measure, things are going to get more muddled, and you won't get anything expected. The moment you reduce your privacy level, you won't get a lot of performance. So.
So actually, in smart buildings, what we found is that there is a vast room for privacy optimization. Because if you consider, like right now we have this room which is in the red temperature, so there is no need to collect any sensor information to control this room temperature to be more comfortable. So there are some, because this is a dynamical system, there are a lot of time slots where we can leverage to mess up the sensor measurements, but we can still control the environment very well. So this is unique to like smart buildings case, but for others, it might be different. So we also explore some other approaches to maximize the privacy utility trade-off. For instance, not only design the privacy preserving mechanism, we perform a co-design of privacy mechanism and the control policy. I also study how can we implement some of the regulations in GDPR in the context of these systems. For instance, GDPR requires us to restrict information gathering for a particular task. So I study how can we minimize the data collection for fixed utility. But I won't have time to dive into this works in more details. So far we have seen some adversaries which try to reveal private information from the sensor measurements. But there are some other adversaries, like the ones that we have seen earlier, which try to inject some bad data to manipulate the machine learning performance. Actually, if you think about it, in the natural data set, even without attackers, there are already some anomalies. Those anomalies are some like rare events. For instance, for system logs, those anomalies correspond to system failure that we want to detect. And for transactional data, those correspond to bank frauds that we want to detect. So how can we have a unified framework to detect all those anomalies, both natural ones and adversarial ones? So yeah, let me talk about an approach. The most successful existing methods to detect anomalous data is to first collect a clean data set and then train a detector on this clean data. And because this detector only sees the clean data, we would expect that it will have different output when it is fed with clean data versus anomalous data. So we can design some anomaly score based on the detector's output. For instance, we can implement this detector as a autoencoder, and that is only trained on the clean data. So when the for clean input, this autoencoder will have low reconstruction loss, and for some anomalous input, this autoencoder will have high reconstruction loss. But the challenge for this kind of method is that in practice, it is really hard to collect a very clean data set, especially in the case of adversarial attacks. Those bad data is really hard to identify even with experts. So here is our idea. So our main approach is to impose some properties on the learning algorithm so that it will forget those bad data in the training set. So what we leverage is so-called differential privacy. Differential privacy is a property of algorithm such that the algorithm output wouldn't change much if we remove or add a training point into the data set. So if we have a differential private learning algorithm, then we know that the output model would not be very sensitive to a particular training point in the database. Let's say this data point is anomaly, then we know that the model will be robust to the anomaly point. So algorithmically, different privacy is often achieved by clipping gradient norm or adding some noise into your training process. And we show that these simple techniques can be very useful to detect the anomalous point, both the adversarial ones and the natural ones. And we achieve the state-of-the-art result for detecting system failures from system logs. So I have also had some other work to look at from the attacker side. So how can we review some new vulnerabilities of machine learning pipelines? For instance, I have designed an attack that tries to recover the private learning data from the published model parameters, and we have shown very state-of-the-art result. And I have also looked into how can we infringe the copyright protection of a deep neural network, but I won't have time to talk about those work. So yeah, going forward, I'll be interested in working on this data economy, both combined with theory and practical algorithms. So I have talked about data valuation, although our work has made some steps towards this interesting direction. But there are a lot of open questions. For instance, my work has largely focused on how can we value training data for supervised machine learning models. So how can we extend this approach to some unsupervised learning, reinforcement learning, and some other learning paradigms that drive today's application? And also, I mentioned the Shapley value has some cool property about fairness, but is the fairness perceived and the fairness perceived by human beings? So for that, we don't know. We will need to have some human subject experiment to understand what is the distributive fairness for data valuation problem. And more broadly, it is also needed to design some new data market that can incentivize people to share data and get fair compensation. And also another important problem is that how can we match data set to the right task that it can solve. So we also need to consider the trustworthy analytics. So right now, the work in this domain often considers the attacks or methods that is only robust to particular type of attack. So how can we have a robust model that can be resilient to coordinate attackers? And we know that human is not so vulnerable. So how can we have some biology-inspired defenses? So those are all very interesting future directions. And to achieve all this, we need to make some contribution to both data privacy and machine learning. So with that, I will thank you for your attention, and I would love to take any questions that you might have.
So thanks, Ruoxi, for that interesting talk. And do people have any questions? So maybe I can actually start with one.
Mm-hmm.
So just going back to your stuff about the Shapley value, it seemed like many of the challenges came about because you wanted to work with the Shapley value, and it's nice that it has a lot of theoretical properties, but have you considered moving away and considering a different notion of how each data contributes value to what your final output is, and how is that something you have explored?
Yeah, we have thought about some like the leave one out arrow. So experimentally, we show that it is less indicative of data importance than the Shapley value. Also, it doesn't have this property. And we also recently have an archive preprint showing that actually leave one arrow is inferior to Shapley value because using some theoretical arguments. So we show that if we consider some random subset and actually using Shapley value, the Shapley value is closer to the expected contribution of a data point to this random subset than the leave one out arrow. So both theoretically and experimentally, Shapley value seems more superior.
So with thinking of a data market with different kinds, different classes of participants, large number of data suppliers, perhaps individuals, and then a smaller number of data aggregators who want to present themselves as being worthy of cooperative, of selling data, like receiving data. So the analysis with this notion of optimality of distribution seems to be very specific to a single data aggregator, rather than a group of data aggregators who provide some some notion of varying profit takes
Mm-hmm.
for the primitive data providers to choose among.
Mm-hmm.
And I wonder if there's another level of analysis there, or does it just fall through to talk about a full data market?
Yeah. So for the full picture of data market, there are so many open questions, and the one you mentioned is a very important future question. So we haven't studied the competition between different data aggregators in this work. So here our setup is that we have a bunch of data contributors that are already committed to a single data set, and they committed to work collaboratively to solve a prediction task. And in that case, we want to distribute the profit to different data contributors, but we don't really consider the competitive relationship between different aggregators. Or
yeah. The issues like
mm-hmm.
there was a single label set here.
Mm-hmm.
What if there's an ontology to choose from which provides?
Yeah, but there are some existing work on this. How can we have some demonstrative analysis of data market? And for I believe there is a paper. If you're interested, I can send you over later. So they show that if there are multiple aggregators, actually there is no Nash equilibrium for this data set, and there is some opportunity for free riding. So yeah.
And one other comment.
Mm-hmm.
This is really analysis primarily of data, not say the next level up of being a model economy,
Mm-hmm.
where models are traded perhaps in conjunction with reference to data.
No, we haven't considered yet. But there are some existing work on how can we train a model with a competitive data market. Yeah.
Any other questions? Do you have?
I mean, certainly, where my mind went to earlier was we were talking about using this to produce valuations on data breaches. So I'd imagine that the data breach, you could presumably still use this data. That aspect of the utility is not lost, but if there's IP in that data, then you may have lost that IP as well.
Mm-hmm.
So I was wondering, could you suppose that you could use KNN Shapley to decide if you have a consortium between multiple companies, they've made an agreement to build a model, and then one of the companies faces a data breach, and the other company evaluate how much has been lost in that consortium.
I see. Yeah, this is an intriguing question. The short answer is that we haven't considered that yet. Yeah, let me see. So so there is a IP. So I guess our setting is more like individual has a system or infrastructure to be able to take control of their own data. And if there is not such system, then there are some IP property, and if you lost the data, you also lose the IP. Yeah. And so I want to say that this is purely algorithmic method. So we really need to work with some system researchers to build this system that can allow people to really control their data and can allow people to keep track of how their data is used and who is using it. So for that, so it's still a lot of open questions.
All right, so if there are no more questions, let's have another round of applause for the speaker.
Thank you.